All right. Okay, so I just wanted to give you an idea about my plans for this week and for the exam on Friday. There are several options for reviewing. So there's an SI session tonight in Dunbar 152 at 5:30 tonight. And Mike will have an SI session on Wednesday at 4:30 in the same place. There will be a review session in Lab 114, which is right by the doors here. It's a smaller room, but I hope we can all fit in there. I'll do that at 5:30 on Thursday. And I know we're sort of, we've been going through a lot of material. Chapters 5 and 6 has had a lot of different material in it. A lot of it's related, which is fortunate. And so what I hope to do today is get through some more of Chapter 6. Probably won't finish the whole chapter today. We'll likely finish that up on Wednesday, but whatever I finish today will be what I'll put on the exam. So in terms of what you would need to know for the exam would be through today's lecture. But I'll probably finish that on Wednesday and then use whatever time we have left on Wednesday during class also to just review and go over the stuff for the exam. I hope to have some handouts put on the exam link by Wednesday morning sometime. So if you want to check that before you come to class on Wednesday. Things that we could cover maybe in the review in the class or on Thursday evening. So if you look at some of the old exams, like from 2007, Exam 2 has a lot of the similar topics, but there are a few different reactions that we talked about then from that book that are not in this one and vice versa. So there may be things that you might not have seen on that. I mean, you're welcome to go through it. The layout and the types of topics will be similar. But specific reactions might not be. So what I hope to do is put together a list of reactions that you need to know. Hopefully that'll help you study from. And if I can put together some other targeted things for you to study, hopefully that'll help. So look for that sometime Wednesday morning before class. If you go to the web page, click on the exams link. I'll post it there. I won't put it on the lecture page. Okay, the Chapter 5 problems we'll be finishing tonight, so if you haven't completed that. Has anyone had problems with Chem if they've used the cluster computers? Hearing no problems? Good. It looks like people are doing it. I do see a fair number of students who haven't started the problem set yet. So if you haven't done that, you should get busy. I think we're a little bit behind. You might have seen I put the Chapter 6 Learn Smart module on, and it won't be due probably until sometime later, even after the exam. But that Learn Smart, and we're getting a little behind in terms of the Learn Smart and the homework with the chapters, and we have an exam coming up. So hopefully after spring break and when we come back together, we can try to keep that a little more on schedule so that you're actually doing those learning before the exams, hopefully. Okay, so that's the exam coming up. I just wanted to remind those of you who did watch the video, if you haven't watched the video of Friday's lecture when we weren't here in this class, you should do that because there's a lot of information that I talked about. So we discussed the electrophilic addition chemistry to alkenes. And actually there are several types of addition reactions that we can do with alkenes. This is a reaction which is essentially the reverse process of an elimination reaction. And hopefully as we see more examples of this, you'll be able to connect those and figure out why one reaction would go one way and not the other. We talked about this reaction, which is the hydrogenation of alkenes. This is actually not an ionic reaction per se. It's catalyzed by a transition metal. And really what I want you to get out of this particular reaction is not necessarily the details of the mechanism. However, if you know the mechanism, it helps you remember the outcomes of these reactions. So in this case, what happens is we have alkenes and hydrogen gas, which can react to form alkanes. But the problem with this reaction is the high energy required to break the hydrogen-hydrogen bond. And that's where a catalyst comes in, such as palladium bound on carbon, shown in this example, that helps to activate the hydrogen and the double bond as well in a kind of a complicated mechanism. The result of this, what you really should remember, is that hydrogen plus a transition metal catalyst and an alkene adds those hydrogens across that double bond, and does it in a very specific way. And because of the nature of the mechanism of this all happening on a surface, the addition or the face of the double bond, which those hydrogens add to, are very well controlled. So hydrogens add on a double bond in a syn fashion. That is, they're adding from the same side. And so if you have a case where you have a ring, for example, and you do hydrogenation of an alkene, in this particular example using a platinum catalyst, the hydrogens end up cis in the product. You don't get the trans product. So the important thing to remember is the type of reaction. What are the products and what is the stereochemical nature of that product? It is specific to give the only product as being a syn addition. Okay. I discussed also how to think about the electrophilic addition to a double bond of something like hydrogen halide, like HBr or HCl. This is a two-step process, which is electrophilic addition of the proton first to the double bond. And so if you think about this reaction, let's look at each step individually. The rate determining slow step is protonation of the double bond by transferring the proton to the double bond. So the electron density is in the double bond, in the pi bond. And the hydrogen is the electrophile. So remember when we talk about polar reactions, we have electrophiles, those things that are electron deficient seeking electrons. So in this first step, it is the double bond and the electron density in that double bond. This is the nucleophile in that reaction. Okay, the nucleophile. So you generate a carbocation. We've talked a fair amount about carbocations in different contexts. And that carbocation then reacts with the bromide in the second step, which is a faster step than protonation. The rate determining step is the first one. This is a faster step, and so you get to the product by transferring now the bromide attacks the carbocation, and then that forms the carbon-bromine bond. So if I separate this out into this step, what's the nucleophile and what's the electrophile? In the second step. Well, the electrophile is what's electron deficient, right? And the nucleophile is what has the electron density that's forming the bond. So in this case, in the second step, the bromide is the nucleophile, and the carbocation is the electrophile. Okay? I want you to start getting used to recognizing the various roles of reactants in reactions. And when we look at a specific step, you should be able to identify what role each partner plays. Okay? Okay, there are some aspects of regioselectivity in this reaction. That is, if you add HBr across a double bond, right? It's a two-step reaction, and we form a carbocation. And in the previous two chapters, we talked about this a lot as well, Chapter 4 and Chapter 5. When you form carbocations, it preferentially makes the more stable carbocation, right? So the more substituted carbocation will be more stable. So when you do this reaction of addition of an electrophile, something plus to a double bond, that group which is plus, in this case it's an H plus, that's going to add to the side of the double bond with the most amount of hydrogens already, the least substituted, because when you do this, you'll generate a carbocation now on the more substituted. So notice the H plus that I added ended up on the end, leaving the intermediate with a plus charge that's more stable. That leads to the formation then of this product where the bromide in the second step adds to the more substituted carbon. You don't get the product of the bromide adding to the least substituted carbon. So this is a generality in all the different kinds of reactions that we work with, which involve carbocation intermediates or radical intermediates. Those are both more stable if you have more substitution. So you see that also in the case with these examples, where if you add H+, you're going to form a carbocation, in this case in the middle carbon, and if you add H+ to that cyclopentene structure, you're going to make the carbocation in the more substituted carbon. That's where the bromide in these cases are all ending up. Okay, that regioselectivity was observed by a Russian chemist called Markovnikov, and he made a rule which he follows to state the observation that they found when they examined these reactions. And it's restated here given the knowledge we have now of the mechanism and the reasons why. When you have a two-step mechanism, protonation occurs to form the more stable carbocation preferentially, because that's the lower energy pathway. Okay. So in this case, if you have an unsymmetric double bond, proton adds to the least substituted carbon, giving the plus charge or the electron deficiency on the more substituted carbon. That's a lower energy path than the other way around. Okay, and we can do this addition or electrophilic addition to double bonds with other things besides hydrogen halide, besides HBI or HCl. Because again, this reaction is simply a two-step process, which is more general than that. I tried to focus on what is nucleophile, what is electrophile in each of the steps. And it's exactly the same thing in this case. If we take a double bond in the presence of an acid and water, so this is an aqueous solution of sulfuric acid, we get the same kind of process. If we have a strong acid, you're going to protonate the double bond, and preferentially you're going to form you're going to break the double bond, form the bond to the carbon to the hydrogen with those electrons on the least substituted carbon. That leaves the deficiency or the plus charge on the more substituted carbon. So our plus charge is a tertiary carbocation here. And the hydrogen that came from the acid, I'll highlight here, ends up on that end of where the double bond was. Okay? If this were HBr, bromide would add. So now we have generated in the first step an electrophile that's looking for a nucleophile. Well, in this case, there is no bromide around. There's no bromide nucleophile to add. There's potentially a sulfate nucleophile, and if you have nothing else present, sorry, that should be SO4 minus, HSO4 minus. If there's no other nucleophile present, well, perhaps that could add, but as was pointed out in this chapter and in Friday's video, that's a very difficult process to do because sulfate is not a very good nucleophile. It's not very polarizable. Water, however, is a good nucleophile. That's the only other nucleophile we have around in this reaction mixture. So if you can remember the generalities of mechanisms, then you can make sense and reason it out. Even if you've never seen this before, you should be looking for what has electron density, what's deficient of electron density. So in this case, we would add water. That would form this oxonium species, and then to get to the product, it's simply loss of the proton. So notice, we consumed a proton in the first step, and we release a proton in the last step. So actually, technically, this is an acid catalyzed process. We regenerate that acid in the reaction. Okay, so it's an acid catalyzed hydration of alkenes or addition of water across a double bond. And I want to try to put this into some broader perspective here because if you think about it, this addition of water with a proton acid catalyst across the double bond forms an alcohol. And in chapter 4, we talked about alcohols and protonating them and exchanging it for a bromide. Or we talked about in chapter 5 an alcohol, protonating it and having it eliminate to form a double bond. That's the reverse of this reaction, right? So if all these things can go one direction or the other, and if it's all happening in both directions equally, right? If the reaction is going to favor the side which is the lowest energy product, okay? That's the thermodynamic nature of the reaction, if it's an equilibrium. Fortunately, we have ways to manipulate reaction conditions so that we can choose whether we want to do an elimination reaction to go to the left side, or we do an addition reaction and go to the right side. Okay, and we do that based on the other things that are present. So if you recall from general chemistry, I hope you learned about Le Chatelier's principle in equilibrium reactions, right? This balance from left to right is going to be dependent on the energy of the materials. But if you're removing, for example, if you have water on this side of the reaction and you remove it from that reaction as it's being formed, that's going to shift the balance of the equilibrium to the left. Okay? So under very strong acidic conditions without water or a significant amount of water present, you're going to do elimination reaction. So if you just take this alcohol and dissolve it in concentrated sulfuric acid, it's going to eliminate. Or if you heat it up and boil the water out as the reaction's going, it's going to the equilibrium will lie to the left, and you'll form the product of elimination. If, on the other hand, you take sulfuric acid and dissolve it in lots of water, and you increase the amount of water, that shifts the equilibrium to the right. And that's how we manipulate this process. Okay, and so when we've looked at these different reactions, you might have seen slightly different reaction conditions, where I just say acid or HBr, but I didn't really talk about water, or I say aqueous sulfuric acid, or something in water. If you think about this mechanism again, we have a double bond which is being protonated by an acid catalyst. So this generates a carbocation. I'm going to put the hydrogen here. That's where it is in the product I've drawn. Okay, a carbocation. And then as we just saw, addition of water, I'm going to write both those steps in one. Addition of water and then loss of the proton will form the alcohol. The reverse of this is the protonation of the alcohol. I should do that in a different color. I guess it doesn't matter. And then in this case, elimination of the hydrogen, right, of the proton. So you should know the details of the forward or the reverse reaction. We've seen these carbocations before. Okay. If I take the alcohol with sulfuric acid, I protonate it to form the carbocation intermediate, and then eliminate the proton to give the double bond. If I were to do this with, instead of H2SO4, I did it with HBr, what else could happen? Well, that's a process. So if we have other nucleophiles present, you can form products like this. Right? We saw that if we have these kinds of halogenated compounds, there's another way that we can do elimination, right? If we have a strong base. Something like this. So all these types of reactions and what possibilities could happen, they really are all connected in a way. It all depends on the specific conditions, what you have present at any given time, how a reaction will, the pathway will proceed. Okay, and so if you can look at this in a little bit more global perspective, it'll help you to see reactions more clearly and make sense of things that maybe you haven't even seen yet. Okay, and hopefully as we go on and talk about more types of reactions, some of these concepts will connect in that way. Okay, the selectivity, this addition of water to a double bond catalyzed by an acid. I left out the water here, didn't I? This should have water present. The hydration of a double bond forms selectively the more substituted alcohol, because that's the carbocation where that OH is. That's where the carbocation was formed, right? You don't get the other product where the OH group has added to the end. As chemists, we want to be able to control everything, right? We want to have the ability at will to synthesize either this secondary alcohol, or if we want, we want to be able to make this primary alcohol. But given these kinds of reaction conditions, and the fact that we know if we do an acid-catalyzed hydration, Whatever adds plus to the double bond, in this case a proton, goes to the least substituted carbon, and whatever is the nucleophile in that second step adds to the more substituted carbon. There's no way to manipulate that. We don't have control of that. So how can we do this? How could we switch this selectivity or switch the product preference? Well, we just need to think of other ways based on the same chemical principles in how to do that. And one way that we have to do this is a reaction which we refer to as a hydroboration reaction. Because like the acid-catalyzed hydration, we added something plus to the end, leaving the carbocation in the middle, and then something minus added to the middle. Well, if we can find something else plus that's not a proton but could be converted into an oxygen later, then we might have some control over that. And one of those reagents are boranes, boron compounds that have a hydrogen bond. Okay? It could have other alkyl groups on it, or it could have other hydrogens on it, but the nature of this species is very different than HBr, or H2SO4. Okay? H2SO4 has the hydrogen being in a plus state. Okay, if you think about sulfuric acid, this is plus and this is minus. So hydrogen is the electrophile to react with the nucleophilic double bond. Well, these reagents which have boron switch that around. Why? Why do you think boron would add to the double bond in the way I've shown here? What would be the nature of the boron reagent that would make you think that? Yes? Boron is electron deficient, right? It's to the left of carbon on the periodic table. It has an empty orbital. It only has 6 electrons around it. So boron is seeking electrons. In the case of a protic acid catalyst, the proton of the acid is seeking electrons. In this case, we have boron with an empty orbital. It's seeking electrons. And so it is, if you think about the nature of this reagent, it's the boron atom, not the hydrogen, which is the electrophilic species. So in that way, you can make sense of this regioselectivity. The mechanism is slightly different, but it also has to do with the size of the boron. But if you want to remember it this way, you can think about this as being the thing that was positively charged that added, and the nature of a BH bond. Hydrogen is more electronegative than boron, so it's got the electrons. And this is the minus group that added. Okay, so it makes sense with what we know about plus and minus adding to a double bond. As I said, the mechanism isn't quite like that. It's a little different, which I'll show in a moment. But once we do that, now we have a way to take a double bond, and we put a hydrogen atom on the more substituted carbon. And we have something besides hydrogen on the least substituted carbon. And fortunately, that gives us a handle to then convert the boron into an oxygen. And if you just treat this with hydrogen peroxide, after you form this, treat this with hydrogen peroxide under basic conditions, that converts the carbon-boron bond to a carbon-oxygen bond. And so the net result is, by doing this process in a slightly different way, we have a way to selectively get an alcohol product that we could not achieve doing acid-catalyzed hydration. Okay? So because we've gotten the opposite regioselectivity, opposite of what Markovnikov would predict in the acid-catalyzed addition, this is often referred to as the anti-Markovnikov product. And so this allows us now greater tools for synthesis. Right? As an organic chemist, I can choose the acid-catalyzed method if I want the first alcohol, or I could choose this method if I want the second alcohol. Here are a little more details of this reaction. I don't really expect you to know that. I wouldn't have you regurgitate the details of this mechanism, but I want to point out that the way this adds, it does have significant consequences with regards to the stereochemistry of the result. If we form a carbocation, by protonation with an acid, then you generate a p orbital at that carbocation with the lobe above and below. If water adds, it could add from either side. So you actually end up with a mixture of products if you have something like a ring. However, what's observed in the case of hydroboration is that the boron and the hydrogen are adding on the same side of the double bond. So if you have a ring like shown here, you get hydrogen adding, and again, it's anti-Markovnikov in terms of the substitutions on the carbons, boron on the least substituted carbon, hydrogen on the more substituted carbon, and that's where the alcohol ends up once we oxidize it. But they also end up cis, the hydrogen and the OH that have added, end up on the same side. So this is also a syn addition. Okay, so when we have rings, that becomes important because you only get selectively one product. Okay, and as this suggests, what I've drawn here, the mechanism doesn't go through free carbocations. What happens is that the bonds forming and breaking all are happening at the same time. And so if you're interested in the details of the mechanism, I'll show that in a second. These reagents, what you'll see listed on reactions, your book uses a couple of them. One is borane. This is BH3 is called borane. Okay, and borane often comes in a solution of tetrahydrofuran. This is tetrahydrofuran, that molecule. It's abbreviated THF. And unfortunately, in chemistry and in many other sciences, we end up with lots of abbreviations to make things easier for us, but it's a language we have to learn. But that borane THF is a stable form of borane. So what's happening here is simply a complex, which is a oxygen Lewis base, and boron is a Lewis acid. That helps stabilize it, but when you get it in solution, that will come apart, and you'll get the boron with the empty orbital to react with the double bond. But this allows it stable enough that we can actually buy these reagents in solution and use them in the lab pretty easily. Another form of borane is this, and it's kind of a strange structure. It's a little hard to depict the actual Lewis structure of this because if you think about this, this is a dimer. I'll just break it like this. This is a dimer of two BH3 molecules. And what's happening is that this is really not two bonds to hydrogen, but the two electrons, say the two electrons in this, are actually being shared for all three atoms. And the same thing, the two electrons here are being shared for all three atoms. So it's not like completely satisfied, but it does help to stabilize as well. Your book lists this reagent, B2H6, being done in a solvent called diglyme. If you're interested in that, that's not really easy to understand IUPAC name, but this is the structure of diglyme here. It has ethers. By the way, this functional group, when we have carbon, oxygen, carbon, this is an ether functional group, and there are several in here in this particular molecule. These just help to solubilize these reagents. And you'll notice about both diglyme and tetrahydrofuran, they're not like alcohol solvents. There's no OH group. OH groups and borane are not compatible. So these simply don't have OH groups. So if you've been confused about what some of those terms in your book mean, THF stands for tetrahydrofuran, an ether solvent, and diglyme is a little bit more complicated ether solvent. Okay, this is actually how the reaction proceeds. As I said, boron, and in this case BH3, it has an empty orbital seeking electrons. The pi bond of a double bond is where the electron density is, and that's where the reactivity takes place. So boron is the electrophile, the double bond is the nucleophile. And as that comes close, the boron orbital overlaps. At the transition state, you might have something like a complex, well, right before the transition state, where the boron is beginning to interact and change where the electron density is in that double bond. And then what happens, to actually get the hydroboration to add across the double bond, that boron slips over to allow the hydrogen to form a bond and the boron to form a bond. Okay? It does so in a way which actually is a 4-atom transition state. So the boron, hydrogen, carbon, carbon make like a 4-membered ring in that transition state. And it all happens at once. So this is a little different than other electrophilic additions in that it's not a stepwise process that forms an intermediate carbocation. But the net result is the same. If you think about boron as being the plus thing that added, the plus thing adds to the least substituted carbon, and the minus thing, the hydride, adds to the more substituted carbon. Okay? Does that make sense? That explains the fact that they're both adding at the same side of the ring, because both bonds are being formed at the same time. And since the boron hydrogen is connected, it has to be from the same side. And once that happens, this is a little complicated, and I'm putting this up there for those who are interested in how the oxidation works. You won't need to know this for an exam or anything, but it helps to explain how that alcohol happens. So the peroxide, under basic conditions, forms a peroxyanion. A peroxide is a molecule that has an oxygen-oxygen bond. Oxygen-oxygen single bond. So in this product, the borane is still electron deficient. So what can happen is that the peroxide anion can react with the boron to form a bond. Okay? And that bond, because of the weakness of the oxygen peroxide bond, that undergoes a rearrangement here to exchange the boron carbon bond for an oxygen carbon bond. And that's the oxidation of the carbon which is taking place. Then water or hydroxide simply breaks hydrolyzes the BO bond, and you end up with the alcohol. So it's a nice process. This reaction maintains the position of where the boron carbon was. That's exactly where the boron oxygen bond ends up, and in the same direction on the ring. So we haven't changed any of that in this process. Okay, hydroboration. Another related process is the addition of other kinds of electrophiles. And very electrophilic reagents are the halogens. So bromine molecule or chlorine molecule or iodine molecule. Anytime you have a halogen-halogen bond, that's an electrophile. And you can kind of think about it as the equivalent of, say, an X plus and an X minus. Okay, I put them in quotations because you're not really generating a free X plus. What happens is once the electron density in the double bond approaches the bromine-bromine bond, for example, then it begins to polarize so that you can essentially attack it like this. So again, this double bond is the nucleophile in the reaction. Okay. Your halogen molecule, Br2 or Cl2 or I2, F2 does a whole lot of other things, very reactive. That becomes an electrophile. Because it's reacting first with an X plus, if you will. Okay? So if you go beyond, we've talked mostly about adding H plus to a double bond, but anything plus reacts in the same way as a proton. So what happens in this reaction is you generate an intermediate, which has X plus added, and then X minus will add to the other side, and so you end up with an X and an X. Okay. Now there's an interesting observation about this reaction, because if you compare this directly with the addition of HX instead of XX, right? If it's a proton, you would draw, oops, let's just put this here. Okay, you would draw this, right? So if you add something plus, in this case I've added X plus, based on the mechanisms we talked about for protonation or addition of HBr, you might draw Br plus adding, and then a plus charge, and then Bx minus adding. Okay? But there's an observation you have to explain if you think about the reaction in that way. If we have a cycloalkene, like cyclopentene, and we react it with Br2, the product we get out is the stereoselective. It is a product where the bromines are on opposite sides of the ring. Okay, that's very different than addition of HBr or addition of borane or hydrogen, H2, through that mechanism. This is a selective reaction, which is an anti-addition across the double bond. So one of the bromines adds to the top, the other bromine added to the bottom. Okay? One of them had to add as a plus group, and one had to add as a minus group. So what's happening in this reaction? How do we explain that given what we know so far about reaction mechanisms with alkenes? Doesn't make sense, right? If we form a carbocation, that X minus should add on either side. So there's something more to it. Carbocations are high energy species. If there's any way at all to avoid forming a carbocation and stabilize it without having the C plus, it'll try to do that. And as we know, if we form carbocations and it can rearrange to more substituted carbocations, it'll even do skeletal rearrangements. So in this case, what happens during halogenation is that the reaction occurs, yes, we add Br plus to this, but it's actually not forming a single bond. You're forming two bonds across the double bond, and it's actually a three-membered ring. This adds to form a bromonium ion. Notice the plus charge, if you calculate formal charges, the bromine with two bonds would have a formal plus charge. So a better way to draw this, let me just draw the bromine up here and how these electrons flow. Remember, these all have lone pairs around them, right? This is why bromine can do something different than a proton. A proton is just an empty orbital, s orbital. A bromine, when it's breaking this bond, so the electrons in the double bond react with the bromine, right? That will form this bond on the left in this example. That kicks off then the bromide. But instead of leaving behind a plus charge on the carbon next to it, one of the lone pairs from the bromine satisfies that plus charge. That's where we get the second bond. And it does that again because this is a lower energy. The bromonium ion is lower energy than the carbocation. So in any reaction, it'll always adopt the lowest energy pathway, right? That has consequences to the stereochemistry of the reaction. Because if we have a bromine now which has bonds to both of the carbons, it's not stable, okay, because it has a formal plus charge on it. But the nucleophile in the second step, the bromide, can only come from one side of the ring because there's a bond on the top that's blocking it from the top side. Does that make sense? So because we have this three-membered ring, this bromonium ion, okay, you can't add the second bromine in the form of bromide to the same side. It has to come from underneath and break. That's why it's selective for forming the bromines on opposite sides, or anti-addition across the double bond. Okay? And you really only see this when you have a rigid ring, so you know that they're on opposite sides.
Bromonium ion has an extra pair to donate to form that bond?
So the bromine has, each bromine has 3 lone pairs on them, right? Overall, they start with 7 valence electrons. So the bromine molecule looks like this. So when the electrons flow from the double bond to form a bond with bromine, that's breaking the bromine-bromine bond. And then it's one of these lone pairs which makes the second bond. And that's why it has a formal plus charge, because it's had to use one of its lone pairs. Okay? Just like oxygen. Like if you take water and you protonate it, right? Where does that proton go? To one of the lone pairs on oxygen. Well, that's what's happening. One of the lone pairs on bromine is forming the second bond to help stabilize the carbon. Bromine, since it's a larger atom, more electron density around it, it can actually stabilize the plus charge on the bromine atom better than the carbon atom, because it's a bigger atom. This works the same if it's chlorine, Cl2, or if it's iodine, I2. And as you can imagine, it gets easier to form that plus charge the bigger that atom is. Iodine works even better. Okay, so remember our discussion of recognizing the reaction partners in each step of a reaction. In this case, the alkene starting material is the nucleophile, and the Br plus is the electrophile in that first step. Okay. Now in the second step, this bromonium ion has a weak bond. Actually, if you want to think about that as partially positive on the carbon. What's the electrophile? What's the nucleophile? Well, the bromonium ion in the second step is the electrophile. It's electron deficient. It's the bromide, which is the nucleophile. Okay? So what do you think would happen if I, instead of just treating this with Br2, I took this reaction and treated it with Br2 in water? Now there's two competing nucleophiles present for that second step. Here we form the bromonium ion, but then if you have water present, that could react a slightly different way. So water can compete with bromide in the second step. And if water adds, and then you lose a proton, you end up adding an OH group. So that's interesting, isn't it? Again, think about the comparisons. If we do acid-catalyzed hydration, we've added an H plus and an OH minus, technically, across the double bond, right? Because we had an acid in water. Well, in this case, we have a bromine electrophile, Br2, so we had a Br plus and an OH minus across the double bond. It's similar to a proton acid-catalyzed hydration, but we've just used something else plus to begin with. And because of the nature of the Br being different than the proton, which allows the formation of a bromonium, it also affects the stereochemistry of that nucleophile as well. So Br and OH will be trans. Okay? I want to make sure you're all following this. Is everyone up to speed on all this that's going on in these reactions? Again, think about the connection between the different reactions we're talking about and the similarities in generalizing it to nucleophiles and electrophiles. So this also shows you that the regioselectivity that we would expect is also held true. Even though we don't form a free carbocation, even though we form a bromonium ion, we still form the reaction where the plus group added on the least substituted carbon in the end, and the minus group, in this case OH, added to the more substituted carbon. Even when we do this Halohydrin formation. And why do you think that would be? Can you explain that? If you're not forming a carbocation, if you're forming this three-membered bromonium ion, why would it matter? Let's think about that. So again, the reaction would occur to form an intermediate bromonium ion. Okay. And then in this case we have water, which is adding, it could add to this carbon and break that bond, or it could add to this carbon and break that bond. Okay, why does it add to the more substituted carbon? This is the nature of reaction. You have an answer?
The oxygen in the hydroxide is more electrophile than the bromine.
Well, right, it's not more electrophile. The oxygen is a better nucleophile than the bromine. Because in the second step it's a nucleophile. But here's the deal, right? You have water. Pardon my terrible drawings here. You have water. It could react to form, to react here on that carbon and break that CBr bond. That would give the product which is not formed. Okay, we don't observe that. What we observe is the reaction of this OH group attacking that carbon and breaking that bromine bond to give the substitution that we would expect normally of a, quote, Markovnikov type product. The plus group added to the least substituted carbon, the minus group, in this case OH, added to the more substituted carbon. That's because even though we don't have a free carbocation, the different substitution at the two carbons the bromine's attached to have different amount of plus charge on them because these are polarized bonds. Let me try to clean some of this up here. Okay, so each of these bonds are polarized towards the bromine, right? Bromine has a plus charge. You're going to polarize the bonds between it and the carbon. Well, it just happens that this one's going to have a greater plus partially positive charge on it because it is a longer bond because it can more stable, it'll have a little more positive density. And this is one of the problems when we switch to thinking about valence bond models to molecular orbital models, right? Because we're really talking about where the electron density is over the whole molecule. Still, you're going to have a little bit more positive charge on this, more substituted carbon. Even though it's not a free carbocation, we can still use the same logic that that's where the more substituted carbocation would be. And that's, we can utilize that to help explain the result we get. Okay? So the net result of all of this discussion is that if you generalize this to think about something plus adding, something minus adding, it follows Markovnikov's observations about regioselectivity. Your book doesn't have a chart like this, but I think it's useful to step back and take a look at all of the types of reactions we've talked about with addition of some electrophilic species to a double bond. Okay, so if we have an alkene, which is electrophilic, we're adding something, and in quotations because they're not necessarily free cations or anions, we're adding something plus to the least substituted end of the double bond. We're adding something minus to the more substituted end of the double bond. There are slight differences in that mechanism depending on what that plus group is. Okay. In this case, I've generalized A. A could be a proton, in which case you generate a free carbocation. Or A could be a halogen, in which case you form a halonium ion, which is bridging. Either way, if you take a look at all the reactions we've talked about, addition of water catalyzed by acid, H plus and OH minus. Okay. We refer to that as the Markovnikov selectivity because that's the electrophilic addition. Well, we could switch that if we add a B plus and an H minus. But overall, in the end, after the oxidation, it's really the equivalent of an OH plus and an H minus if we think about Markovnikov selectivity. But since it's an OH and H have switched, we refer to it as anti-Markovnikov. HX or X2 in a water, something plus, adding to the more substituted, or sorry, least substituted, something minus, adding to the more substituted. Okay, on Wednesday we're going to try to finish up chapter 6 and then do some exam review, and hopefully we'll be all set for Friday's exam.